In this chapter, we learn about the two-sample z-test for averages. So, as an introduction, let's suppose that an elementary school is assessing whether to switch from a standard approach to teaching reading to a phonics-based approach. To help them make the decision, they compared the average reading test score of a group of students taught in the standard way to an average score of a group of students taught using the phonics approach. So, how would they determine which method is better? So what we're going to do is we're going to learn about hypothesis tests for two samples. Now remember, a test of significance, a hypothesis test, helps us determine whether the results could have just occurred by chance. And we always say, like, if the null is true. In this case, if we're talking about two groups and comparing two groups, the null would always be that they're the same. Or in this case, the null would be that there's no difference between the approaches. So we're going to see, well, is the difference in what we see in our samples, could that have occurred just by chance if there was really no difference in how the reading approaches worked? So far, we've seen hypothesis tests involving one population. Often, we're interested in comparing averages from two populations. So what we're going to do is we're going to draw a sample from both populations, and then we'll have two sample averages and we'll have two sample SDs, and also two sample sizes. So what we'll do is we'll use a two-sample z-test for our averages if we want to know if there's a difference in the two population averages. And what we'll do is we'll compare the difference in the two sample averages. Our test statistic will be z equals our observed difference minus expected difference over standard error for the difference. Now this is also just introduction. We'll get to our official page in a minute. And you might have noticed, like, okay, I don't really know how to find observed difference or expected difference. We'll get to that in a sec. Standard error for the difference. That's something kind of new that we haven't done yet. So the standard error for the difference, if you want to compare these two populations, what you have to do is you're going to find each standard error of the first sample and square it, do standard error of the second sample, square it, and take the square root. So that kind of combines both standard errors to kind of give you a group or some kind of pooled standard error. Now, in this class, our null hypothesis will always be that the two population averages are equal, that there's no difference. So then the expected difference of the sample averages will be what? Well, if you think that your two population averages are the same, you'd expect your two sample averages to be, well, probably the same, right? So if our two population averages are the same, we'd expect the sample averages to be the same, give or take a little bit of chance error. Obviously, they won't be exactly the same. But our expected values would be that they'd be the same, and then what's the difference between two things that are the same? The difference will always be 0. So if the population averages are the same, you expect the difference between the sample averages to be 0, give or take some chance error. Just also remember your standard error for your average, that's always equal to SD over square of the sample size. So we're going to find that standard error for the average for both of those samples. This is our two-sample z-test for averages. We use this test if we want to compare two population averages. To do this, we are supposed to have two independent samples. Remember, independent samples means that they don't affect each other. So the two independent samples is what all of our math is based on. Now, it does turn out that you could also compare two randomized groups if you were doing a controlled experiment with this. The two randomized groups do have a little bit of bias compared to just normal, simple, random samples. However, there's a little bit of bias one direction and then a little bit of bias the other direction, and they kind of cancel out. So we can do this for two independent samples, or if we have two randomized groups. Again, those two randomized groups should be independent. They still shouldn't be affecting each other for this to work. Also, for both groups, the sample size has to be at least 30. Because we are going to use a z-curve, which means that our sample sizes have to be big enough for the central limit theorem to work, so at least 30. Now for a little bit of preliminary work, you have to find the standard error for the average for both samples separately. So we'll do the standard error for the average will just be equal to SD over square root of the sample size. Because we have two samples, we find that for each sample. Then we'll do all of our normal preliminary work for the difference. Because we're comparing two populations, we have to find our everything for the difference. So we'll find observed difference. It'll just be the first sample average minus the second sample average. You just find the difference. Expected value for the difference is 0. That's again because if our population averages are the same, if the null is true and they are the same, then we'd expect the difference to be about 0. And the standard error, we need some way to kind of group those two individual standard errors together. So the way they came up with to group it is you do the square root and you'll do the first standard error squared plus the second standard error squared. Then our test statistic stays the same as what we've been doing. Z will just be equal to the observed difference minus expected value for the difference over standard error for the difference. And the p-value is just going to be the area in the tail or maybe tails under the standard normal curve, just like what we've been doing. So we just use the z-curve. So if you think that the population average A is less than the population average for B, you find the area to the left. If you think the population average A is greater than the population average B, you find the area to the right. And if you think that they're just different, you find the area in both tails. Now this will only work if you always write everything in the same order with A first. Otherwise, this less than to the left isn't going to work for you. So you'll notice as we go through the video, I'm very careful to always write everything in the same order. 2 remarks. If the population means are equal, we expect the sample averages to be about the same. So we expect the difference to be 0. That's why expected value for the difference was equal to 0. And secondly, we won't worry about a small sample size z-test for 2 samples in this class because that gets more complicated than we want to deal with it for this class. So first example, do newborn baby boys weigh more than newborn baby girls? Consider the following independent samples and perform an appropriate statistical test. So you'll notice for boys, it gives us our sample size, our average, our standard deviation. Girls, sample size, average, standard deviation. You might notice here that they have different sample sizes. Sometimes people, well, most semesters, at least one person will say, wait, isn't that bad? It's not. So different sample, or let's put it this way. It's okay if the samples have different sample sizes, as long as they are both over 30. So our sample size of 40 was bigger than 30, our sample size of 35 was bigger than 30, so we're good. So first up on our preliminary work is, remember, we're going to have to find the standard error for each one individually. So the standard error for average is equal to SD over square root of sample size. So our SD is 0.96 over the square root of our sample size, which is 40. Gives me 0.15. And the SE for the average for the girls is going to be 1.17 over the square root of 35, which gives me 0.198. Okay, so those are my 2 standard errors. For my null hypothesis, remember, null is always going to be that the population averages are the same. So we'll say the average weight for boys is the same as for girls. And any difference we saw in the sample averages is just due to chance error. For your alternative hypothesis, then, that's kind of what you want to show. We wanted to show that, let's see, the baby boys weigh more than baby girls. So the average weight is higher for the boys than for the girls. And just to kind of make a note, I always like to write down what's the question asking. We're trying to ask, basically, is the average for the boys, is that bigger than the average for girls? Notice up here I had boys first, so when I wrote this statement, I wrote boys first, and that's going to help me figure out how to do my p-value later. Okay, test statistic. I found the standard error for each of them, so now let's go to our preliminary work of observed difference. Well, that's just the difference in your sample averages. So my first sample average is 7.47, minus my second one of 7, which gives me 0.47. Again, because I did boys first, I have to make sure I put the boys' average first. Expected value for my difference. Well, if the population averages are the same in the null hypothesis, we'd expect the sample averages to have a difference of about 0. And standard error for the difference is the square root of the first standard error squared plus the second standard error squared. So let's see. This will be the square root of 0.15 squared plus 0.198 squared. 0.15 squared plus 0.198 squared. Then take the square root of all of that. I should get 0.248. Now I've done the preliminary work. I know my observed value, my expected value, and my standard error. So now z is always equal to your observed, and I'll write a diff because I'm doing differences, minus the expected value of your differences over the standard error of your differences. So my observed is 0.47 minus 0 over the standard error 0.248. I get 1.895. So I was about 1.895 standard errors away. So let's find a p-value. Now, because up here we wanted to know, we wrote boys first, so we want to know, are the boys bigger than girls? So since it's bigger, we will shade to the right. So here is z equals 1.895. I want the area to the right. I look for 1.895. So the closest would probably be this 1.90. Oh, but that 97.13, that's the area to the left because it's a z table. So this was 97.13%. So I'll do 100% minus that 97.13%, which gives me 2.87%. So my p-value is 2.87%. Now when I look at that, 2.87% is smaller than 5% significance level. So we will reject the null hypothesis. Have you ever noticed it's always reject or fail to reject the null hypothesis? Then we'll write our conclusion. We have evidence. So whenever we have a small p-value, we have evidence, and then you just write your alternative hypothesis again, so that we have evidence that the average weight of all the boys is greater than the average weight of all the girls. Now, obviously, the boys' sample average we picked was higher than the girls' sample average. So some people might look and say, why do we need a hypothesis test? Obviously, the boys were higher. But that's because even if your population averages are exactly the same, we would expect to see some difference in the sample averages just due to chance error. Chance error just means based on which sample we picked. And so we would never expect them to be exactly the same, even if the population averages were the same. So the question is, was the difference in the sample averages so big that we believe it couldn't be just chance error? And instead, the difference must be due to a real difference in the population averages. So in this case, yes, we're like, well, there was only a 2.87% chance that we'd get such a big difference in the sample averages if the population averages were the same. And that seems pretty unlikely, so I'm going to guess that the population average for boys was actually bigger than the population average for girls. Next example. Visa wishes to compare the spending habits of its preferred Visa cardholders with those of American Express Gold members. So a random sample of 400 Visa cardholders gives an average monthly charge of $45, SD of $212. The American Express members, a sample of 385, has an average of 523 and SD of 185. Let's test to see if American Express cardholders spend more. So when I go through, I like to first make notes of everything. So for Visa, we have a sample size of 400. We have a sample average of 485. And we have an SD of 212. For our American Express, we have a sample size of 385, a sample average of 523, and an SD of 185. That's all the information they've given me. Notice both of my sample sizes are big. They are much bigger than 25, so we're good there. So my first preliminary step, after I write down all that information, is I have to find the standard error. So standard error for the average is always equal to SD over square root of sample size. So my SD is 212 divided by square root of 400 gives me 10.6. And over here for my American Express, standard error for my average is going to be that standard error of 180, or the SD of 185 over the square root of 385, which would give me 9.43. Now that we have both standard errors, I was going to say we could go on to do more of our work, but we should probably stop there and write our actual hypotheses. So my null hypothesis is always going to be that the population average spending is the same for Visa and American Express. The alternative hypothesis, okay, let's see. What is that? Let's write our note up here. Notice I wrote Visa first, so I'm going to come up here and say, is the Visa average bigger? Let's see. No, that's not what they want me to test. They want to see if American Express spends more. So that would mean the Visa average is smaller than American Express. Now notice here, this is very important. Because I wrote Visa first here, I have to write Visa first here, and I have to say smaller instead of like doing American Express is greater. So Visa first here means Visa first here. Okay, back to our alternative hypothesis. This would be that the population average spending for Visa is less than American Express. Okay, so we did our hypotheses. Now let's do the rest of our preliminary work. Our observed difference is just subtract the two sample averages. So that will be 485 minus the other sample average of 523. Again, I did the Visa stuff first. So this is negative 38. Our expected value for the difference, well, if the population averages are the same, we'd expect the difference to be about 0. And standard error for the differences, we'll do square root, and we'll do the first standard error squared plus the second standard error squared. So square root of, let's see, my first one is 10.6 squared plus 9.43 squared, which is 14.18. Now we can find Z. Z is always equal to your observed difference minus expected value for your difference over standard error for your difference. So the observed value is negative 38, expected value is 0, standard error is 14.18. And when I divide this, I get negative 2.679. Okay, looks like I've unfortunately run out of space, so let's come back up here to find our p-value. Okay, when I look at what I wanted to find, I said I think that the Visa average is smaller than the American Express, so I'm going to look in the left tail. So this is Z equals negative 38. I'm going to shade in the left because, again, we said that we think Visa is smaller than that. Oh, sorry, Z is not negative 38. Z is negative 2.679. Go to your normal table. Negative 2.679, probably this one. Looks like the area is 0.35%. So 0.35%. So my p-value is 0.35%. Okay, that is a small p-value. It is less than 5%, so I will reject my null hypothesis. And we found evidence that the American, or that on average, the American Express spends more than Visa, or that Visa spends less than American Express. So again, it's very important to always keep that same order throughout your entire problem. So if you wrote Visa first, make sure you put Visa first every time. Now, as a side note here, because this always shows up on the test, let's interpret the p-value. So to interpret the p-value would be something like, there is only a 0.35% chance of seeing such a big difference in our sample averages if the population averages were the same. So this is the same as what we've been interpreting before. It's saying there's only a 0.35% chance of getting what we got in our sample, except in this case it's samples, so seeing such a big difference in our sample averages if the population averages were the same, so if the null was true. Okay, so a little note here about making errors. Because we are dealing with chances, we can make mistakes. That means sometimes we will reject the null hypothesis when we shouldn't. If we use a 5% cutoff significance level, we will accidentally reject a new hypothesis, we will accidentally reject a true null hypothesis 5% of the time. Which means, like, if we did 100 hypothesis tests, we'd expect to actually reject a true null that we shouldn't reject 5% of the time, or 5 of those 100 times. Now, sometimes we fail to reject the null hypothesis when it was false. So sometimes we reject the null when we shouldn't. Sometimes we fail to reject the null when it was false, and so we shouldn't have. Unfortunately, there's no way to tell for sure whether we're correct or not, just like when we did confidence intervals. Okay. You hope that you had one of the hypothesis tests that worked, but you don't really know for sure. But luckily, bigger sample sizes do make us less likely to make errors. And if I took different samples, I would get different sample averages, and therefore different z-values, and therefore different p-values, and maybe even different conclusions based on different samples, which is why 5% of the time we'll actually make that error just based on which hypothesis test, or based on which sample we happen to pick. Okay, example 277. A simple random sample of 400 families is taken in Washington, D.C., and the average of the 400 incomes is $61,000 with an SD of $9,000. Another simple random sample of 900 families is taken in Philadelphia. The average of the 900 incomes is 57,000 with an SD of 15,000. So they want to know, are they richer in Washington than in Philadelphia, or is the sample difference just due to chance error? And then we'll also look at, if our result is statistically significant, is it also practically significant? So my null hypothesis is always going to be that the population averages are the same. So the population average of Washington is the same as the population average of Philadelphia. The alternative is what I want to show. So they said, are they richer in Washington than in Philadelphia? So the population average in Washington is higher than the population average in Philadelphia. Now that we have that, let's write down some of that preliminary work that we've been doing. So for Washington, we would have our sample size equals 400. Our, let's see, sample average equals 61,000. And my sample SD equals 9,000. In Philadelphia, we have a sample size equals 400. Oops, over here I typed 40. 400. 400, my sample average equals 57,000. And my sample SD equals 15,000. Okay, let's see. Let me just double check that I didn't write anything else wrong. Okay, that's what they gave me. Let's start on our preliminary work. So the standard error for the average for Washington is equal to, again, my SD over square root of my sample size. So my SD is 9,000 over square root of 400, which gives me 450. For Philadelphia, my sample error for the average, standard error for the average, is the SD of 15,000 over square root of 400, which gives me 500. Oh, sorry, apparently I did not look close enough. The sample size in Philadelphia was 900. Which means, for my standard error, I should be dividing by the square root of 900 instead, which does give me the 500. Now we can find our observed difference, which is just subtract your sample averages. So again, notice I put Washington first, so I'm going to do Washington first. I did Washington first there. So we'll do 61,000 minus 57,000 divided by, no, not divided by yet. Sorry, thinking of the wrong class. 4,000. That's the observed difference. Our expected value for the difference is just always equal to 0 because we're assuming the population averages are equal. So we'd expect to get our sample averages about equal, so the difference would be 0. And the standard error for the difference is equal to the square root of standard error, the first standard error squared, plus the second standard error squared. So in our case, this will be 450 squared plus 500 squared, which gives me 672.68. Now we can find our test statistic, Z. Z equals observed for your differences minus the expected value of your differences divided by the standard error of your differences. So our observed difference is 4,000 minus my expected value of 0 divided by standard error of 672.68 should give me about 5.95. For my p-value, which way am I going to shade? This is 5.95. Let's see, we did Washington first over here. We said we think Washington should be higher than, so we will shade to the right for higher. Let's go to the normal table and look for 5.95. Notice 5.95 is going to be way off here off the chart, which means that chance, because it's so far off the chart, is going to be about 0. So my p-value is about 0%. Now, if I wanted to interpret that, this means that we have about 0% chance of seeing such a big difference in our sample averages if the null is true. So if the null is true, if the population averages are the same. Now, almost 0% is obviously a small p-value. So we will reject the null hypothesis. And we have evidence that the average income of all people in, let's see, Washington is higher than the average of all people in Philadelphia. Now the other question is, was it practically significant? Okay, well, is it statistically significant first? So because we have a small p-value, our results are statistically significant. This means that we are pretty sure there is a difference. But now you come down to practically significant. So practical significance means it would actually matter in real life. So what was the difference? It looks like our difference we saw was $4,000. So would $4,000 a year make a difference to you? Now that's just practical, that's just personal opinion. I would probably say yes, I could do at least something with $4,000 a year. So I would say that would be a practical difference. It's practically significant. Example 278. 100 freshman women and 81 freshman men are given the study habits and attitudes survey. Their scores range between 0 and 200. See, for men, they have an average of 120, SD of 28, and men have an average of 85, SD of 35. Let's come here and fill in what they didn't tell me. They didn't say the sample size, so sample size for women equals 100, and sample size for men equals equals 81. So now that I know that, I'll just kind of put this here instead of having to write it down below. Test the hypothesis that there is no difference between men and women for this survey. So the null is always that they're equal. So the population average for women and men is the same. The alternative, notice, let's see, what did it say? It said there is no difference. So no difference. It didn't say which one they think is higher. It didn't say anywhere which one they suspect is higher. So the alternative is that the population averages are different for the men and women. Anytime you see that it's just different, that's going to be a two-tail test. We're going to look at both tails when we find the p-value. Okay, preliminary work, I'll just do it up here. My standard error for my average is equal to SD of 28 over square root of sample size, which is 100. So that should give me 2.8. And my other standard error is going to be equal to 35 over the square root of 81 equals 0.43. All around that to 0.44. Wow, I don't know what I put into my calculator. That's actually supposed to be 3.89. Okay, now let's do our observed difference equals, let's see, we'll just subtract our two sample averages. So we'll do 120 minus 105, which gives me 15. My expected value for the difference, again, is 0. And my standard error for the difference. You have to kind of pool or kind of group them together. So we'll do the square root. We'll do the first standard error squared plus the second standard error squared. So we'll do the square root of 2.8 squared plus 3.89 squared, which should give me, so that gave me 4.79. Now we can do our actual test statistic. Z equals observed difference minus expected value of the difference over standard error of the difference. So our observed difference was 15. We expected 0, and the standard error is 4.79. Which gives me 3.13. Now for my p-value, remember how we said this is different? So my p-value will be both tails because we said it's different. We didn't know which way to shade. So if z equals 3.13, this over here would be negative 3.13. We'll shade to the left, we'll shade to the right. Let's look up the area to the left of that negative 3.13. So 3.13, I guess this would be the closest here, at 0.0186%. And then this area would have to be 0.0816%. So the area in both tails, or my total, is 0.0816% plus 0.0816%, which gives me 0.1632%. So that is my total p-value. That means that we would have a, let's see, 0.1632% chance of getting such a big difference in our sample averages if the null hypothesis is true, or in this case, if the population averages were the same. Okay, let's see. P-value 0.1632% is smaller than a 5% significance level. So we will reject the null hypothesis. And we would say that we have evidence that the, let's see, what were we looking at? That the population averages are different for the men and women. And once again, as a side note down here, unfortunately, if you do a two-tailed test, all you can say is whether the population averages are the same or different. So the test itself doesn't actually say which population average is higher. Yes, I can use a logic and come up and say, okay, which one was higher? Oh, the women were higher. But that's not what my hypothesis was. That's not what I went in looking for evidence for. I can't actually say that as my conclusion. I would just say we've shown that they are different. The reason why is people go into these studies and they don't actually really know which way they think is going to be bigger. And so they're just kind of testing to see if it's different or not. Once you find that there is a difference, you might do another study and try again to see if you can show that maybe the women are higher, if that's what you think.